Hello, my name is Kerry King. I'm a research associate at the Center for International Energy and Environmental Policy. That's part of the Jackson School of Geosciences at the University of Texas at Austin. And I'm also part of the Weber Energy Group. Today we'll be talking about the water requirements for transportation in the light-duty vehicle sector. In this first slide, I'll discuss the amount of water required to drive on a car on different fuels. The units for displaying the results are gallons of water per mile traveled. This provides a common framework for understanding the water quantity impact of different technologies and resources and describes the results in a way that is understandable to the consumer. For each fuel and technology, this supergraphic displays both water consumption, indicated by the leftmost bar, and water withdrawal, indicated by the rightmost bar. The water required for mining and farming parts of the life cycle are shown in red. The water required for processing and refining parts of the life cycle are shown in green. The results of this graphic assume an equivalent vehicle fuel efficiency of 20.5 miles per gallon for the average light-duty vehicle fuel efficiency. The bottom two sections of each column represent a minimum water quantity, and the highest value indicated by each column represents an upper limit to the water requirement. Furthermore, the black dots in each column of the graphic represent average or nominal values for water consumption and withdrawal for each of the fuel combinations of technology and resources. First, we'll look at conventional fossil fuels. Typically, about 0.1 gallons of water per mile or less are consumed for driving on petroleum, gasoline, and diesel. The water consumption for driving using a compressed natural gas vehicle is even lower than for petroleum. For driving on gasoline and diesel from unconventional fossil fuels, the water consumed is higher in the range of 0.3 or 0.4 gallons of water per mile. This includes converting coal and natural gas to Fischer-Tropsch liquids. An important feature to note for using oil sands and oil shale to make gasoline is that the mining portion of the life cycle, indicated by the red area, represents more than half of the water consumption for each. Thus, the water impacts are localized near the mining site. For example, the Athabasca region of Canada and the region at the border between Colorado, Utah, and Wyoming for the oil shale. When we look at hydrogen fuel cell vehicles, assuming the hydrogen comes from electrolyzing water, the water consumption is driven primarily by the water consumed at the power plant that is generating the electricity. This water consumption is mostly attributable to evaporated water for cooling steam-based coal, nuclear, and natural gas power plants. Thus, if the average U.S. mix of power plants is assumed, the approximately 0.4 gallons of water per mile are consumed for driving a fuel cell vehicle. If we assume that the electricity derives from a non-thermal heat plant, such as wind power or photovoltaics, or a power plant that is steam-based but has dry cooling, then the water consumption is very minimal with less than 0.1 gallons of water per mile, as the main requirement is then only for the water feedstock required for the electrolytic process itself. Using steam methane reforming to extract hydrogen from natural gas also has low water consumption per mile, similar to conventional gasoline. Electric vehicles and plug-in hybrid electric vehicles consume between 0.2 and 0.3 gallons of water per mile, with the bulk of the water consumption due to power plant cooling, just as with the fuel cell vehicles. Again, if the electricity for charging the electric vehicle comes from a dry-cooled power plant or a non-thermal process, then the water consumption is practically zero. Now we look at two of the most common biofuels used in the United States: corn grain-based ethanol and soy-based biodiesel. What is shown in this graphic is only the irrigation and process water parts of the life cycle, and not the water associated with evapotranspiration of crops, which is a very important piece of information and a focus of future studies. As is clearly seen from this graphic, in which the y-axis must be broken to show larger consumption values than for all other fuels, biofuels from irrigated crops consume 2 orders of magnitude more water in gallons of water per mile traveled than the other fuels. The average water consumption for driving an E85 flex fuel vehicle, for example, on irrigated corn ethanol is 26 gallons of water per mile. And for soy biodiesel, this value is just under 10 gallons of water per mile. However, only approximately 15 to 20% of the corn crop in the U.S. is irrigated to any level. So if we look at the water consumption from corn ethanol without irrigation, the values are in the same range as the other alternative fuels and technologies such as fuel cell and electric vehicles, as well as unconventional fossil fuels that are converted to liquids.
Feel free to come back to our website, weberenergygroup.com, for more updates on all the students' research, our latest publications, and the things we're up to these days.